welcome everybody. Slightly delayed start. This is my fairly standard talk on surveying the sky for radio galaxies. I've done this more times than I can count, and I keep updating it and putting new things in. I will try to keep to a sensible time because I can essentially talk about this forever. But I'll hopefully keep to something like an hour or 55 minutes, and then we can have time for some questions.
That's fine, Martin. That's what we normally do. But don't feel worried about the time. It is open-ended, but that's usually what we do. Questions, I think you prefer at the end, yes?
Press questions at the end unless it's a really burning one, or you can't see something, or
okay. I'll let you know. Thank you.
Okay, great.
So I've had a problem with my gear.
Please mute everybody.
Okay.
All right. So what I want to do to start with is just explain what the title is about. So I'm going to have a very brief introduction to what I mean by surveying the sky by radio galaxies. Then we'll talk about the history of the subject, and then I'll come on to work that we're doing now in Hertfordshire and around the world towards this, and finally I'll be talking a bit about what's going to happen in the future. So standard sort of picture, really. Let's start then with what it means to be surveying the sky. So I was glad that we started off with the comments about Lord's Bridge. So I did my PhD here, not actually sort of here in this picture, but definitely this was a big part of the landscape when I was working there. Sorry, keeps advancing without me wanting to do. So when we talk about surveying the radio sky, we're talking about looking at the sky with instruments like this that are designed to look not at a specific patch of the sky, but at very large areas of the sky to find out what's actually there. Now, as everybody knows, we have a pretty good idea of what's out there in the optical sky. We have had for thousands of years. Everybody can go out and they can look at constellations that are pretty much the same as have been seen since the start of human civilization. Surveying the radio sky is a little different because we didn't even know there was a radio sky until the 20th century. We didn't know there was anything to see. And it took quite a long time for us to even get as far as being able to see what was out there. So the first radio surveys were done using an instrument that looks like the thing up in the top right-hand corner here. This is not an old biplane, which is what it looks like, but a radio antenna, the radio antenna used by Carl Jansky in 1933 to discover radio waves from the Milky Way. So the brightest source in the sky for us, apart from the sun, in radio waves is the Milky Way itself, and you can just see the whole galaxy. And that's what you're seeing in this image of the whole radio sky, which is what you see below. Color-coded image of the radio sky. You can see a big band across the center. This is in galactic coordinates, and what you're seeing is the Milky Way. And that's really what's dominating. I'm not actually going to talk about the Milky Way very much, but the Milky Way is a really bright thing in the radio sky. If we take, perhaps I'll go back. If we imagine taking a tiny patch of that survey, this overall survey this was done in the 1980s, and just zoom right in on a patch where nothing is happening, away from the Milky Way, and look at what that looks like. This is the sort of thing you see. There's an odd object out here, which is a moon. I put that in for scale. You can't see the moon like this really in radio waves. It doesn't look quite the same, but everything you can see behind the moon, as it were, is a real radio image of the sky taken from one of our older surveys. And so you can see that the sky is full of little dots. Well, it's probably no surprise, but what's interesting is what these dots are. These are not stars. In fact, if you look at some of them, you can see that they're extended. They're not like a star. They're not just one little thing. They're actually got size and shape. And in fact, everything you see here pretty much is a galaxy. So when you start looking deep into the radio sky, you see that the radio sky is full of galaxies producing radio emission. So why do they produce radio emission? There are two types of galaxies that produce radio emission. So one is this kind of thing, normal star-forming galaxies. So this is Messier 82, and fairly nice objects to observe with reasonably straightforward kit to obtain. Here it is in the optical. It looks very pretty. You can see the you can see this kind of blue disk of newly formed stars. You can see some dust. You can see some red stuff here, which is hydrogen alpha. So all sorts of cool stuff is going on. If you observe this with a radio telescope, and this was done using mostly the Merlin array, so the one that's based at Jodrell Bank, with telescopes around the UK. You see this. So I'm just going to flip between them. You can see that you're seeing radio emission from the disk of this galaxy where all those blue stars are. And in fact, if you zoom right into this, as you can do with Merlin, because it's high resolution, you can see some little round bits and pieces, and these are supernova remnants. So normal star-forming galaxies with lots of stars in them, the stars form, they go through their life cycles, they die, they explode as supernovas, and the supernovas create energetic particles which generate radio emission, which make galaxies look like this. The reason I'm sort of skipping over this is because this is not actually what I'm going to talk about. Normal star-forming galaxies are not the subject of this talk. So things like the Milky Way, like M82, forget about those. So I'm going to talk instead about active galaxies. And here's an example of an active galaxy. So this is another Messier object, Messier 87, another famous one. But this is the most boring galaxy imaginable, right? You can look at this picture. It's a Hubble Space Telescope one, I think, and it's just a big fuzzy blob of stars, and they're all old stars. You can tell because it's kind of orange, so same sort of color as the sun. There are no really massive, bright blue stars in there. Clearly nothing going on, right? But if you look at this with a radio telescope, you see all sorts of stuff on all sorts of scales. Out to very large scales and down to very small scales, you can see all kinds of complicated things centered around the idea that there's something at the middle and there is stuff coming out of the middle. So you can see here, this is the center of the galaxy, something coming out here. And you kind of zoom into it, getting closer and closer to the center. And of course, famously, when you get right down to the center, the Event Horizon Telescope has discovered this structure down in the middle, which is supposed to be the shadow of a black hole. It's not, you're not seeing the black hole here, you're seeing the shadow of the black hole. The black hole is kind of in that dark point here. But what you're seeing here is radio waves that are coming from the center of this object, this radio galaxy. So things like M87 is what we're talking about. Here's another famous radio galaxy. This is a thing called Hercules A. And what I'm showing you here is a composite radio optical image. So this takes a little getting used to. Excuse me, the background picture here is Hubble Space Telescope optical. So you can see big fuzzy galaxy in the middle. See where my cursor is. This is an elliptical galaxy, big fuzzy blob of stars, many other galaxies around it. Some of these are actually sort of companions of this galaxy. If you look at the radio image, which is this kind of pinkish stuff that looks kind of like a couple of ice cream cones coming out of the galaxy. This was taken with a very large array radio telescope in New Mexico, and it clearly is doing something very different from what the stars are doing. And you can see, again, the idea that you've got these very thin lines coming out of the center of the galaxy, going out in opposite directions and sort of going into the ice cream cones. And one of the things you've got to realize about this is that this must be happening on a really huge scale, because this is a whole galaxy. So this big elliptical galaxy is probably 100,000 light years across, which means the scale of the overall object is probably 1 million light years. There is something making these radio waves coming out on scales of millions of light years. And so that's what radio galaxies are. For historical reasons, we call these things radio galaxies, or sometimes radio loud active galactic nuclei. And that's what the talk is about. How do you find these things and how do they work? People sometimes ask, why is there radio emission? Why are we looking at this in the radio? And the only bit of physics, the only bit of real physics in this talk is to say the radiation process here is a thing called synchrotron radiation. So we've got very energetic electrons, and they're moving around in magnetic fields, and that gives rise to the radio emission. We know it's that because of the spectrum and polarization of the emission. So I'm not going to talk about how they get that way, because this is not a detailed physics talk, but that's why they shine in the radio. The other thing people sometimes ask is, what do they sound like? And this is probably inspired by Jodie Foster sitting next to this telescope, the VLA, with a pair of headphones. We don't listen to them. We just make pictures. So what we're doing when I talk about a map of the radio emission, I'm talking about how strong the radio emission is towards a certain point and mapping that out. Okay, so now that you know what I'm talking about, let's take the historical trip that I said we'd take back to the start of the discipline of radio astronomy. So I showed this picture already. This is the array for the 4th Cambridge Radio Sky Survey, done in the early 60s, if I remember rightly, or the late 50s. And now we can look at this and we can say, what is this object that we're looking at? So this structure here is a telescope, and actually these curved parts of it are mirrors. So the principle of a radio telescope is the same as a normal telescope. You're catching the radio waves and you're trying to bring them to a focus, and then you're trying to record what you see at that focus. You may be more familiar with the sort of dish type things. You can see these in the background. This is the old 1 mile telescope. But the principle is the same, whether it's designed like a dish or like a sort of cylindrical array like this one. You're catching the radio light, you're bringing it to a focus, and you're trying to measure it. Up at the top here in this image, you can see, sadly broken now, the dipole array that was catching the radio light and actually measuring the intensity of it once it was focused by the metal structures. So that's the sort of thing that we're building here. We're building radio light catchers. They can be quite big. They need to be quite big because the wavelengths of radio light that we're talking about are meters. So the wavelengths are the same size as a person. And that means everything has to be on quite a large scale. So radio surveys were kicked off after the Second World War by a bunch of bright people who came out of wartime Britain with probably with a truck or two full of X-radar kit that nobody wanted anymore, and a sense that they could do something interesting that wasn't just about finding German bombers, and a healthy disregard for authority. One of these people was Martin Ryle, who was the founder of the Mullard Radio Astronomy Observatory, and won the Nobel Prize at some point in the 60s, 70s for the discovery of radio interferometry. And that's the big story that that underpins a lot of what I'm talking about today. It's the discovery that you can make one big radio telescope by joining together many different radio receivers. And not only that, but the bigger you make it, the better it is, not just because you're collecting more signal, although you are, but also because a bigger telescope gives you a higher resolution. So the further apart the elements of your interferometer, the higher the resolution you can make. This is good because it's also true that as you go to longer wavelengths, so to lower frequencies in radio, you get lower resolution as well. So you've got a way of beating that problem by just making your telescope bigger and bigger. And this was Ryle's insight, and that's why he built, building things like called the 1 mile telescope, the 5 kilometer telescope. These were all basically saying, this is how big we're going to make it, because this is what we're trying to do with it. So imagine you're back in the late 50s, early 60s, and you're looking at a radio survey. What do you see? So this is taken from one of the images from, I think, the 3rd Cambridge survey. This was the one where there was a lot of contention with Hoyle about the steady state versus Big Bang. This is all being done with the aim of dealing with cosmological problems that were key at that time. So if you look at this image from this paper by Patricia Leslie in 1961, you can see looks quite modern, actually, in many ways. You know, you've got that same sort of arrangement of dots that I showed you in a previous picture. And these dots represent the radio sources, and the size of the dot represents the strength of the radio source. And they're mapping out where in the sky these radio sources are. So that's all great. They skipped a bit here with the Milky Way because it's too bright, but there's plenty of radio sources here. So you might say, well, we've got a few hundred radio sources. What's the problem? The problem with this was that their resolution was still very low. So they didn't really know where on the sky these radio sources were to any degree of accuracy. The sorts of measurements they were actually looking at, this was all fairly sophisticated work for the time, but what they were really looking at was these traces, well, which looks more like an EEG than something you get from a telescope now. You're looking at, you can see these peaks representing individual radio sources, and you can see, because this is in sidereal time, that the size of these peaks is pretty big. So we're looking at positional accuracies that are pretty low, of the order of, several arc minutes, which is really not good enough, because the thing that you really want to do with this radio source is, if you want to understand what they are, and not just to prove Fred Hoyle wrong, if you really want to understand what are the radio sources and how they work, the first thing you've got to do is find the optical galaxy that goes with them. And you can't do that if you're told, well, there's a radio source over there in the sky somewhere, in this sort of half a degree or so, there'll be one there somewhere. Because an optical astronomer comes back to you and says, yeah, there's quite a lot of galaxies in that bit of sky. Which one do you want? And you don't have an answer. So once all the cosmological fun had died down, people started building bigger and bigger radio telescopes with the aim of actually studying these radio sources. And so the 5 kilometer telescope, that was the last one that Ryle built, had enough resolution that you could actually go in and say, what do these individual dots look like? Let's make a map of what they look like. And when you started to do that, as people did and started to do in the late 70s and 80s, they started to see this kind of structure. And you recognize this, I hope, as the same kind of thing I've shown you much prettier pictures of. This is a radio galaxy. It's got this double structure, got bright points at the end. And so right in the middle here, there's a little dot. And under that little dot, there is an optical galaxy, 19.5 magnitude galaxy. And so now we know what this thing is. It is a distant galaxy. It's a redshift of about, this one's about 0.5, I think, which was distant for the time. And we were able to say, Lang was able to say in 1983, this is what this radio source is. But you notice that 22 years had elapsed in this, between one slide and the next. It took them 22 years to go from, we know there's a radio source there, to we know what galaxy it goes with. We're going to come back to this because it's always been a big problem. So, as I said, what happened in the 70s and 80s was people started to say, we don't need any more surveys. We've got lots of radio galaxies. We've got hundreds of the things. What we need to do is study them in lots of detail. And instruments like the 5 kilometer telescope, but much more so, this thing here, the Very Large Array, were designed specifically to give you detailed studies of individual objects. So this is I'm sure everybody has heard of the VLA. It's probably the most famous radio telescope there is. It is an array of 27, 25 meter dishes. It lives in New Mexico in a big flat plain that doesn't have very much else going on. And what you're seeing here is it's in its compact configuration. This is an aerial view, of course, and you're seeing it in a compact configuration where all the dishes are quite close together. But you can also see, I hope, that they're on rails. And so this telescope literally telescopes. It expands out. You can make it up to about 30 kilometers from end to end, which gives it very high resolution and makes it a really good instrument for detailed studies of radio galaxies. It's hard to get a sense of the scale of this thing, but it is massive. So here's one of the dishes. This is taken by me the only time I was ever out there. This is the one of several pictures of my wife in this talk. In fact, right here, standing in front for scale. But the dish is 25 meters across, right? So it's like a swimming pool across. Standing in that, it feels like quite a big thing. and you've got 27 of these things, and they weigh hundreds of tons, and it's a pretty impressive piece of scientific instrumentation. It has the very, very wide set of capabilities. It can go from very low frequency to very high frequencies. So from 74 megahertz to 74 megahertz to 43 gigahertz, almost a factor of 1,000 in frequency. And at the high frequency end, if you work in the biggest configurations, you can get sub-arc second resolution at gigahertz frequencies, which means essentially it's the same sort of resolution as a ground-based optical telescope. So that's good. You might think, well, why doesn't everybody always use it in the highest resolution mode? There is a technical issue with that, which is important for the rest of the talk, which is that the VLA's sensitivity to extended structure is also dependent on the configuration. So if you make it in its biggest configuration, it's got very high resolution, but it can't see the large-scale stuff in the sky. If you make it very small, it's got terrible resolution, but it can see the very extended stuff. So it was designed to be used actually in a mode where you observe several times in different configurations and put them all together, but that's quite cumbersome and quite hard to get the telescope time, so people often don't. And the other thing about a telescope made of dishes like this is that the field of view is quite small. What that means is that it's only really sensitive to stuff that's directly in front of the dish. So you can't efficiently map large areas of sky efficiently and sensitively. So, however, where we came in was we said this was a great instrument for understanding the physics of individual objects, and we had a few hundred radio sources from these surveys from the 60s and 70s, and so people went off and they studied those with high resolution with the radio telescopes. And this is an image. So this image we've seen before. As I said, the radio structures here are from the VLA, and you can see we started to understand what the physics of this is. So we believe there's a central black hole, a supermassive black hole in the center of all of these galaxies, billions of solar masses, and that the structures that we see coming out from the center of the galaxy are jets of energetic plasma traveling at speeds close to the speed of light. They travel out, they interact with the external environment of the galaxy, the diffuse gas in groups and clusters of galaxies, and as these jets come out from the black hole, they push out into that medium and they form the lobes. We understand this in the context of active galaxies, which is something that we know about more generally. They were discovered in the radio as well, but now quite well known from their optical properties. So things like quasars. We understand that this central black hole can be responsible both for radiation coming out from very close to it and also from jets, and possibly both at the same time. And the details of how that works, we think we sort of understand. And the hand wavy slide here is this is an attempt to show pictorially a quite complex model where the rotation of the black hole drags space around, twists up magnetic field lines, and pushes energy into the external medium that comes from tapping the spin of the black hole. So the black hole spins down, but energy is pushed out along these jets of magnetic field, and they pick up matter, and then they produce the jets that we see. And I think we've had quite a lot of success in modeling how those large scale structures, remember I'm talking about things on scales of millions of light years, how those structures evolve. This is work that I did some time ago with a colleague at UH. So this is a visualization of a numerical model of the evolution of a radio galaxy. So you should imagine this is the fastest time lapse you've ever seen, by the way, because this whole thing takes about 100 million years. But I've sped it up slightly so we don't overrun. So imagine that over 100 million years or so, you start off with these jets in the center of the galaxy, and they push out, they form those double bubbles, and over time the bubbles grow outwards, and you can see the evolution, and this is what we believe is going on. The interesting thing here in this image is that as well as seeing the radio structure, which is this kind of orangey, yellow, reddish sort of structure, We've also tried to model the structure that you would see in the external hot gas environment. So what does the radio galaxy do as it grows? And so you would predict that it would push out structures and elongate along the jet axis that you might be able to see with an X-ray telescope. Well, this isn't actually a prediction because we knew they were there. But here is an example of one of those structures now seen in a. So now in this image, the blue stuff is X-ray emission, the red stuff is the is radio, and the yellow is optical light. And you can see the red radio galaxy, this is a thing called Cygnus A, has indeed sort of stretched out the X-ray emitting gas behind it. So that allows us to do all sorts of work about environmental impact of radio galaxies, about which I have a whole other talk. But it's really important to understand what these galaxies actually do to their environment. It turns out to be quite crucial for models of galaxy formation and evolution. So we've been able to do a whole bunch of other things to study the matter accreting into the black hole of these radio galaxies. This is yet another one in the center of the Perseus cluster, NGC 1275. We've been able to study them at other wavelengths and see counterparts at other wavelengths to some of the structures that we see in the radio. This is something I worked on a while ago called Pictor A. This is combining X-ray data with data from the Australia Telescope Compact Array. So we know a lot about the individual objects, but you probably realize that since I'm only about halfway through the talk, there must be something that we don't know. So here are some of the things we don't know. We don't really know why some of these active nuclei make jets at all. We don't really know how to even get at that. The stuff that's happening really close to the black hole is very hard to observe. One thing that we'd like to do is look at the sort of statistical properties to say, how does radioactivity relate to host galaxy properties? So what sorts of galaxies make radio galaxies? Actually, we know that it's preferentially elliptical galaxies for some reason, but why? What more information can we get about that? How does the radioactivity affect the host galaxy and its environment? How do the radio structures evolve? We can't see them changing because, as I said, the timescale is hundreds of millions of years, and we don't have that long. But if we had lots of radio galaxies, we should be able to see them statistically at all stages of their evolution. So we should, it's like if you had a snapshot of 10 ants, you wouldn't know very much about ants. If you had images of thousands and thousands of ants doing all the things that ants do, you'd suddenly know a lot more. Even if you never saw them move around, you could start deducing stuff from seeing a lot of them. How do those radio structures evolve with time then? What happens when the jet turns off? It must do, because otherwise the sky will be absolutely full of radio galaxies. All of these questions require you to have more than a few hundred objects to study. So when I did my PhD, I was told we are going to make really beautiful images of all the 3C objects because that's all we need to do. There are 200 of them. Here are your 20. Off you go. And I did. But, and at the end of that, I had the work from the previous PhD students. I had about 40 objects, and I thought there's got to be a better way of studying these things than studying them 20 at a time. And there is, but you need to get the large samples from somewhere. So when it was realized that we really needed large samples from somewhere, people started thinking about doing radio surveys again. So to cut a long story short, people decided to try doing surveys with a very large array. And they run into this problem I mentioned before about the resolution and the sensitivity to extended structure. So a couple of surveys have been done of quite large areas of the sky with a VLA. There's a thing called NVSS, the NRAO VLA Sky Survey, and that was done in the most compact configuration, the VLA. So they detected lots of radio sources. Until recently, this was the biggest radio survey that had ever been done, millions of sources. But they worked at a resolution of 45 arcseconds, which means you've got absolutely no hope of saying what you're actually seeing and how it relates to a galaxy. On the other hand, there was a survey that was done with the VLA in an extended configuration called the FIRST. I can't remember what this stands for. No, it's gone. Some contrived acronym or other. And that's not sensitive to the extended structure. So this image illustrates, one we prepared earlier. Here's a radio galaxy that we know is there in a radio image. This is what FIRST sees, so it misses the extended structure. This is what NVSS sees. It doesn't have the resolution. This is kind of a fundamental limitation of the VLA because of the way the telescopes are laid out. You just can't do both at the same time. And so it's really expensive with the VLA to survey the sky in a useful way. It doesn't stop people trying, but it's really hard to do. So what you actually need to do is build telescopes in a different way, optimizing for doing this survey science. Guess what? That's what we have been doing. So the thing I'm going to be telling you about is LOFAR, one of several next generation radio telescopes, now been operating for quite a while actually. But I still think of it as a big step forward. So it's a low frequency array. It operates at low frequencies from 30 to 200 megahertz. That turns out, firstly, nobody's really done any work in those low frequencies since the very early surveys, because if you're going for resolution, it's easier to do that if you go to higher frequency. And it's particularly good for finding radio galaxies because, as it turns out, those things get brighter as you go to lower frequencies. But low frequencies are hard. There's lots of interference from humans, radio interference. Because the wavelength is very long, you need very long baselines to get high resolution. And you need to put lots of telescopes together, and that means lots of data. So LOFAR, a top-down view of LOFAR looks like this. So you can see it's basically spread across Western Europe, pushing into Eastern Europe somewhat. The core of it is in the Netherlands. We'll come back to this part in a minute, but the international stations are spread over the whole of Western Europe, which we're still part of, whether we like it or not. We in the UK have got one, which I will also talk about. There's one in Ireland and a few in Poland, and these providing 1,000-kilometer baselines, several 1,000-kilometer baselines from end to end, that really give you very high resolution. More of these are coming. So this is an old slide now, but there's one being built in northern Italy, and one in Bulgaria. So we're kind of moving to even larger scales. Okay, so let's do a little bit of a zoom in to see what LOFAR actually looks like. So now we're looking at some Google Earth images. These are slightly older ones, so some of the remote stations aren't there. Zoom in the Netherlands. So here's the relevant bit of the Netherlands. So those of you who know the Netherlands may mostly be familiar with the bit down below the bottom left, where all the population is. Over in the East Netherlands, it's very empty, very agricultural, and perfect for building a radio telescope. So the control center of this is in a place called Dwingelo, which is an old Dutch radio astronomy site, and is in the middle of a national wildlife area. Up here at Groningen is the nearest big city. That's where the data processing is done. But the telescopes, if we zoom in on those, they're all just sitting in fields. And as we zoom in closer and closer, you will be surprised to see that there's absolutely nothing to see till you get really quite close. So when you zoom in onto these scales, you can start to see. I think this is cheating slightly. I think this is an aerial view, not a Google Earth view, because it's easier to see what's going on. But this man-made structure, just a large island. Everything has to be very well drained because it's the Netherlands. You can start to see some strange objects on it, but this certainly doesn't look like the VLA. There are no dishes here. They're just kind of boxes and some sort of grey dots on the ground. Let's keep zooming in. So we'll go into this one here, which is a normal station, and you can see what this looks like. And so you can see these boxes on the ground. Still not remotely clear what the telescope is actually made of, but there's lots of them. Let's go right in onto a ground view. So here's what the low band array of LOFAR looks like. And what you will observe is that this telescope is constructed of plastic sheeting, chicken wire, plastic pipe, guy ropes, and probably something a little bit clever up here at the top of the plastic pipe. In fact, the guy ropes are the detector. They're dipole antennas, and the little thing on top of the plastic pipe is an amplifier. And coax cable runs down the middle of the plastic pipe into the ground and off to be collected. So this is the design philosophy of something like LOFAR. Don't build it out of really expensive 100-ton dishes that cost a fortune. Steel's very expensive. Build lots and lots of things out of cheap, simple components that anybody can put up. No moving parts. So you do everything in software. You decide what bit of the sky you're looking at in software. You combine all of these small antennas that you saw on the ground to make one station, and you combine. So they're like the dishes. The individual stations are like the dishes. Combine the signal from the stations to make the telescope. So when this was mooted, sort of in the first decade of this century, it was going to be basically a Dutch thing, and a number of countries said, well, we'd quite like to join in, and we were one of them in the UK. It was 2009, and money was a bit tight in various ways, and essentially what we did was we got together all the universities in the UK and had a bit of a whip round and said, if you're interested in astronomy, give us a certain amount of money, and we will try to build a LOFAR station, and that will get us into LOFAR. And then the Science and Technology Facilities Council joined us and matched our funding, and so we were able to get enough money to do this, but only just. So we made a compromise. You could get a full service. The Germans got a full service where the Dutch engineers came and built their stations for them. We got this. So I stole this slide from Derek Mackay-Bukowski, who was the guy who actually coordinated the building of the LOFAR station. Basically, what they did was they said, we'll ship you the bits, and you put it together. So flat pack radio telescope. So here we are, putting it together on a lovely British summer's day in 2010. I'm behind the camera in this one. So this is a bunch of us, academics and PhD students and postdocs, trying to assemble one of the many LBA antennas. Here we are, having assembled it. So I'm in this one, looking somewhat younger. Then we repeat this process many tens of times, and we put up a station. And that was the easy part, actually. Just getting it in the ground involved a lot of drilling and hammering and standing things up. But the real work was connecting them all up again afterwards. And you can see on the right, this chap here is very happy because he's just put the last of the hundreds and hundreds of coax cables in. We discovered, we continue to discover stations that were cabled up the wrong way round, but it was a good effort. So this station, which I don't think it's possible to visit, is at the Chilbolton facility, which belongs to STFC down in Hampshire. So if you ever do find you can go and visit it, then this is worth seeing. All right, so let's skip ahead to what science we can do. So I'm skipping over a point where we had built this telescope and we realized we had no idea how to analyze the data, and we had to write a huge amount of software to analyze the data. And so between 2009, 10 or so and 2016 is us trying to figure out how to actually do anything with the data, and failing over and over again and eventually getting somewhere. So this image that I'm showing here is from, it was made by Wendy Williams, who was my postdoc for a while. And I did something very similar about the same time. In this image, you can see what you're seeing here. The reddish colors are the LOFAR survey of an entire chunk of the sky, and this is several degrees across. It's a big area of sky. So you can see that it's finding all of those little dots that we've talked about. It's sensitive to that to all of the things that are there, but it's also got the resolution so that you can zoom right in and see what those things are. And so each one of these lines goes to a little dot here, and you can see that we look at it in detail, and we can see what it is. And many of them are, in fact, the sorts of radio galaxies we're looking at with the double structures. So just this one image gives you as many radio galaxies as in the entire early Cambridge surveys that fed this whole subject for so long. Clearly, this is a huge step forward. The fact that you can both do the surveying and do the imaging at the same time. So we were very happy. And also, the resolution here is about 6 arcseconds, which is it's not brilliant, but it's good enough that you can actually say, in many cases, which galaxy does this actually belong to. So we discovered that we could analyze the data, and so we got kind of cocky, and we decided, let's try to do surveys of the entire northern sky. So we can't really do the south because there are no moving parts, so you can't point LOFAR down at the equator. So you've got to stick to the northern sky. So we thought, well, this is going to take. We did a little bit of a plan. We thought 3,170 separate pointings should cover it, and they're 8 hours each. So, that's doable. And if they'd given us 1.5 years of the telescope time and it had worked 100% efficiency, we could have just got this done, but they didn't. So we have been steadily progressing over the last few years. Here's what we've got as of yesterday evening when I updated this talk. So the green dots here are bits of sky that we've observed and successfully processed and made images. And then various other things, including some where it hasn't worked, but some that are ready to do that we haven't done yet, and some that are in progress, and so on. So you can see that in terms of covering the sky, we've done pretty well. We're avoiding the Milky Way because it's very bright in the radio and it makes things hard. So the blue bars are the Milky Way, and away from the Milky Way, we've done pretty well. So it's pushing on. So the history of this, I'm taking you back to the start. The first thing we did was to just do a little bit of a test field. And this was 2018 or so. So we picked a field where LOFAR should be pretty good. And we decided we will go through the whole process of doing a mini survey of that, processing the data, and getting it out. So the actual field here is this blue region here. So we pushed all of that through, and that's even doing that is a big undertaking. So at that point, it's changed a bit since, but the raw data size at that point was 16 terabytes per 8-hour observation. So those of you who are familiar with terabytes as a unit will know that 16 terabytes is quite a lot. It's not easy to deal with. It's not something you can do on your laptop. It's certainly not something it's easy to stream over the internet. So we're getting this data. So it's processed in Groningen and it's taken off to Amsterdam and stored, and we would get it from Amsterdam and we'd have to get it over the internet and do the processing. We had to calibrate and image the data. So we had that meant we had to figure out, as I say, how to transport the data, but also how to write the software to do it. Pipeline development, so how you go from the raw data to the images. Had to find places to run the actual programs because it takes substantial computing resources. So then you make images, you've got to find the sources in the images, you've got to put those sources together to understand where the real physical objects are. And in many cases that requires people to actually look at the data. Then you want to match them up with optical galaxies. There's a process called optical identification. Then you can find the galaxy properties and their redshifts, and then you know where the things are in the sky. Then you can do some science. So it's a long job. But the results, I think, were really good. This is one of our early images, so it's actually better now. But we were comparing here between our survey the LOFAR survey and the previous VLA surveys, NVSS and FIRST, that I mentioned before. So in this particular image, there's a famous spiral galaxy. I forget which one. It's another Messier object, but I can't remember which one off the top of my head. So you can see beautiful image of this spiral galaxy. There's another galaxy, another spiral galaxy down here, much more disky, seen edge on. There are some radio galaxies. You can see double features here and 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 here, and lots of faint stuff as well. NVSS sees that same stuff, but it doesn't see nearly as many sources, and they look much worse because of the low resolution. FIRST sees more sources, but it doesn't see that spiral galaxy at all. It's just invisible because FIRST couldn't see that extended structure. So we've succeeded in this image. You can see how we succeeded in doing what we wanted to do. We can see both high resolution and also we can see everything that's there, thanks to the design of the telescope. We were very lucky. About the time that we were doing this, Pan-STARRS came out, Pan-STARRS Data Release 1, and this is a very nice survey of the whole northern sky at optical wavelengths. Some of you may be more familiar with Pan-STARRS as a comet finder, but that's incidental to its actual job of surveying the entire optical sky. So we had very nice optical data to match up with the radio. So we did that. Here are just some numbers to give you an idea of the sort of scale of the things. We processed nearly a petabyte of raw data. It took 200,000 CPU hours to make the images, more than that in total through the calibration. And we found a few 100,000 sources, radio sources, including a large fraction where we were able to say this is the optical galaxy that goes with the radio source. This is really good to be able to do this straight away. And I don't want to go into the science here because that's not really the point of the talk so much, but the sorts of things we were able to do once you've got samples of hundreds of thousands of sources is you're sort of competing with the optical astronomers in terms of the way you can deal with the data. You're no longer looking at individual objects. So if you think about famous stuff that you can do with optical astronomy, things like the Hertzsprung-Russell diagram, or the Hubble diagram, where they're based on very large samples, we can start making plots like this one, which is just saying how bright is the optical galaxy and how bright is the radio source. And you can see all kinds of different features on this plot. Without going into detail about what they are, you can't have this view of the population unless you have very large numbers of objects. Otherwise, it's just a mess. You're too limited by the statistics. So we've been able to do and have been improving on this since, very good statistical studies. One of the things that's really interesting from the AGN side, from the radio galaxies, that actually it turns out that they are quite universal. So this plot, which is taken straight out of scientific paper, so it's a bit hard to decode. What I want you to take away from it is that, so this is mass of the galaxy going up to the left. So the more massive galaxies are over here. The more massive the galaxy, the more probable it is that there will be a radio galaxy in it. And that probability kind of goes up towards 1. So the most massive galaxies basically are always switched on. They're always doing something. The nuclei are always generating these jets. And that's kind of something we had no idea of because we just hadn't done the surveys well enough. So these objects are much more common and much more important than we imagined. At the same time, the fact that we've got very large samples means we can go after things that are normally very rare and hard to find and just pick them out again and again. So this is an example that I particularly like because it's based on some work that was done by one of my PhD students, Vijay Mahatma, who's now at Cambridge, and he was focusing on restarting sources, sometimes called double radio galaxies. And this is these are radio galaxies with another radio galaxy inside them. Well, that's how they appear. You can see this on the image. So I've sort of color coded it using VLA data actually to help out. So the yellow contours are the outer lobes, and then the orange ones are the inner lobes in these cases. And you can see quite a few with this characteristic structure of an inner pair of lobes and then an outer pair of lobes. What we think is actually happening here is that the jets have turned off for a while and then they turn back on. And so you start growing a new radio galaxy inside the old one. Eventually they merge. And in fact, quite quickly they merge, probably on a timescale of millions of years, and you can't see this anymore. But for a brief period, you can see one growing inside another. And of course, what that tells you is something about the life cycle. You know, how long can the jets turn off for? How long do they stay off for? Which is quite hard to get at. But we can just pick these things out by looking at images and start doing interesting stuff with them. So we put out a press release and had special issues of ANA and so on. In February 2019, we got great worldwide attention. British press totally ignored it because we were all busy talking about Brexit. But such is life. You can go and see some of the exciting coverage and the images on our website, which is lofar-surveys.org. So since then, we've done some more. So we've released coverage of more than 10 times as much sky. The second data release in February 2022. This had 4.5 million radio sources, so that makes it the largest radio survey ever. 3.2 million CPU hours of processing, so quite a lot of work. 8 petabytes of raw data, so pretty big. I'll just go back to this. So this is just a fly through the second data release data, so you can see the sort of quality. It's really difficult to get a sense of what these data look like because they're just so big. There's so much of it. But you saw the nice spiral galaxy that we started with, and you can see some, I have no idea what that thing is. It looks like a squash fly. There are lots of double radio galaxies coming past. So really high quality data and just vast quantities of it. So one of the things that we decided to do with this particular version of the survey is to ask for citizen science help. And we piggybacked on a project called Radio Galaxy Zoo that had been set up originally to look at VLA data, and we asked for citizen science help to match up the extended radio sources with their optical counterparts. So this is an example of the sorts of thing we were asking people to do. This shows. So this is the Zooniverse web platform. It shows contours of radio emission in yellow and optical images in the colors here that you can see in the background, and we're asking people which bits of the radio source go with which other bits, which is the host galaxy. So in this case, you can see that the host galaxy for this source in the center is almost certainly this thing here, which is a galaxy-shaped blob. But there's another galaxy over here associated with another radio source, and these probably don't go together. They're probably not physically associated. So we're asking citizen scientists to make those choices or help us make those choices. And that took quite a long time. We took about 3 years. We had about 1 million citizen science views of galaxies. But again, the results give us really good statistics. I'm just showing some. These are plots now where you can see millions of radio galaxies and radio bright galaxies all put together, and start doing the sort of scientific selection of what types of object you've got based on that. So really vital that we were able to do this, and we couldn't have done it without human intervention. Okay, so that's where we are now. We're continuing to survey the radio sky with LOFAR. We will get the whole northern sky done. LOFAR is going to have some upgrades, and we'll be doing more of this once the upgrades happened. Just a few things about other stuff that's happening in the future to finish up with. So one of the things that's very exciting for me personally, and here at UH, is that we're going to be following the radio sources up optically, trying to measure spectra. And the reason we want to measure spectra is that they can give us redshifts. Redshifts can tell us how far away galaxies are, and you can't really do any science until you know how far away something is, because then you can convert its apparent brightness to its true brightness and start doing physics. So we've got an instrument, we're contributing to an instrument called WEAVE, which is going to go on the William Herschel telescope. And here it is being moved around, and people looking at it sort of going into place. And when this is commissioned, and it's taking an awful long time, but I'm assured it's going to be working real soon now, we're going to be starting to get redshifts for our radio sources in large numbers, and that'll suddenly make a lot of the science much easier. So that's something that's led from here. One of the things that we're doing right now is to start trying to use the full capacity of LOFAR to make really high resolution images using the international baselines. So this is an image again made by the one at the bottom is made by VJ, who I mentioned earlier, and shows the difference you can get between an image made using only the Dutch part of LOFAR, which is this one here, the little orangey blob, and this is what you get if you turn on the full resolution of the international baselines. The resolution here is about 0.2 of an arc second, so it's very much higher than it's higher than you can typically get from the ground with an optical telescope. But in order to do that, you've got to process the data processing problem is much harder. The international stations are much more difficult to deal with, and we're just in the process of trying to get that up and running and automated in the same way as we did the bulk LOFAR data processing. And I've been working with some people this year to try to get that moving. And finally, the long-term future of radio astronomy is bound up with this thing, the square kilometre array, which again you probably all heard of. And this is going to be, assuming we can make it work, it's going to be huge. So there are some truly amazing statistics about this. They talk about the raw data output here for the SKA. This infographic has got 2 terabytes per second. So if you turn on the all of the SKA and put it all together, you're producing as much as much data as the entire global internet is transporting put together. It's going to be a very difficult data handling challenge, but if it works, when it works, it's going to give it even more sensitivity and even more image fidelity and resolution than we can get with LOFAR. LOFAR won't go away. LOFAR is still going to have a very important role, particularly because SK is going to be in the southern hemisphere. But with the 2 telescopes that make up SKA, the SK1 low and SK mid, we are going to be very much further ahead than we currently are in terms of capability. And so that should be starting to come on stream towards the end of the decade, and there'll be quite a lot of exciting stuff coming out of that. And I'm kind of looking forward to some productive years with that as well. So take-home messages from this. I hope I've tried to explain to you that radio astronomers have been doing sky surveys for a long time. We've been refining our ability to do this again and again, but now with LOFAR and with the SKA, which is optimized as well for surveys, we're going to be in an unprecedented time for this, where we really start to catch up with other parts of astronomy in terms of data rates and volumes of numbers of objects. And we hope that these very large samples of radio galaxies will help us understand how radio galaxies work, how the jets are generated and how they affect their environments. We've already started, and there's a lot more to do. So with that, I think I stop. I'm going to stop sharing because it's nice to see. It'll be nice to see that you're all still there after all this time, and I'm very happy to take some questions.
Oh, wonderful. Thank you. Thank you very much, Martin. Yes, we're all still here.
Excellent. Yes.
And people, please put your cameras back on. Stay muted for the time being unless you've got a question. I'm just going to, first of all, ask everybody, in time-honoured tradition, Martin, we always ask everybody to give you a resounding virtual round of applause, or on the camera. And I'm sure we'll do the same at the end. But can we all give Martin that big handshake and the clap. First of all, thank you very much indeed. Silent hand clap, but there we are for you. Okay, wonderful. I always think that people who talk about objects such as these, such wonderful images, you've always got an advantage over someone talking about purely black holes or
Yes.
some obscure, because it does, whatever else, you get a chance to show some really, really pretty images. They are spectacular, aren't they?
Yes.
Yeah, ice cream cones, dumbbells.
Yeah, yes, all of this stuff. Yes.
Yeah, wonderful. Also, it's a mark of a great presentation when, what I hope is an attentive listener myself, I write down a few questions, and as you go through the talk, I found that I'm ticking them all off, and you've actually answered them all anyway. So, but I do have a couple of questions, and I'm going to hand over to the floor so people get your questions ready. You mentioned that it seems that at the larger scale galaxies, the greater mass galaxies with the larger, perhaps a supermassive black hole at the center, almost invariably or always, I think you said, have these radio emissions. The bigger the galaxy, the more likely it is. My question was going to be at the other end for dwarf galaxies, smaller galaxies, perhaps galaxies with no black hole at all, although we hear these days that pretty much every galaxy does some kind of a black hole. Is it reasonable to infer that some kind of emission is going on even in the most modest and small of galaxies? It's just that they're not so obvious and so loud, as it were.
Yeah, I mean, we certainly can't rule that out. And we know that there are some dwarf galaxies that are actually quite bright. For example, it's just that they're rarer.
Yeah.
So we know the same process can happen in pretty much any type of galaxy. They do seem to prefer the massive ones with the massive black holes, and there's probably some physics reasons why that is. But it's not exclusive. It's a preference. The black hole kind of doesn't care what galaxy it's in. Black holes don't know very much about their environment. They respond to their own, the phenomena they cause are a result of their basic properties, like their mass and their spin, and how much material is falling into them, and how much magnetic field is being sucked into them in the case of jets. So if you get the conditions right, you can have this stuff anywhere. In fact, the same physics probably powers things like gamma ray bursts, where people think that's a collapse of the core of a star into a black hole. Probably the same sort of physics of the black hole is spinning, material is falling onto it, magnetic fields are created, it makes a jet inside the collapsing star. It's actually quite a universal process, and so there's no reason to think that in more normal galaxies, yes, it might be fainter, the black holes might be smaller, the jets might be less powerful, but there's no reason to think it can't happen. And some quite a bit of reason to think it can happen.
Yeah, and you're saying, I think, from that you can get larger black holes in smaller galaxies than you might expect, and therefore they can be more energetic. Even smaller mass galaxies.
Yes, I mean, we were quite surprised. A student of mine a little while ago matched up this LOFAR survey with a catalogue of dwarf galaxies, and we found some very clear cases where the dwarf galaxies were shining quite brightly in the radio. And the only explanation was that they've got a small version of these AGN going on.
Yeah.
There was no other way of making that radio emission. So it can happen. It's just unusual. I mean, it's perhaps, as I said, perhaps every massive galaxy has a bright radio source. Perhaps 1 in 10,000 dwarf galaxies has a bright radio source, but it's a preference, not a rule. I mean,
not a rule of thumb. No.
Yeah.
And the other thing was that lovely model, that animation you had of the evolution of those cones and those jets over time.
Yeah.
As you said, mercifully speeded up, otherwise we would have been around for a long time. I think you gave an example of one that was, a galaxy typical diameter of 100,000 light years, a bit like the Milky Way, but the jets and the cones extending to something like 1 million light years.
Yes.
And you mentioned that the jets are obviously sub-light speed, but a significant percentage, perhaps, I don't know, 90%
yes.
of the. So on that basis, and because we don't see them getting any bigger, I think you said that they seem to have a constant. Would that not imply that somehow, if they're still emitting all the time, and it's not well, we're looking at them obviously as they were anyway, but I kind of trying to get my head around the time. If it's
I think I understand what you're asking. It was a question
emitting for 1 million years rather than you mentioned hundreds of millions.
Yes, it seems like there's something wrong here, right? The jets are traveling at very close to the speed of light, and yet the sources are growing to million light years scales on time scales of 10 million or 100 million light years. So the answer is that the growth of the lobes is not the same speed as the speed of the jets. I mean, it's so imagine thought experiment. You know, suppose you try to suppose you point a hose pipe at a I don't know what could you point a hose pipe at, some sort of flat surface. So point a hose pipe at a flat surface, and that the flat surface is pushed along by the pressure of the water. But does it move at the same speed as the water does? No, it would move a lot slower.
Yes.
Right. So the jets are pushing the front of they're going out into the medium, and they're pushing a discontinuity into the medium. But the speed of the discontinuity moves is not the same as the speed of the jets. What must happen then? Well, the material must do what the hose would do if you pointed it at a brick wall, sort of splashes back. All right, so you get this kind of splashback, and that's what actually inflates the lobes. If you imagine having a jet that was where the front end of it was moving as fast as the jet was moving, that's more like a machine gun.
Yeah.
Right. So you'd have to shoot out little blobs, and they would just travel ballistically through without responding to the external medium. And that can there certain types of jets found in protostars are more like that. Actually, they're more like machine guns or cannonballs or something. You know, discrete ejector that shoot off with high density.
Continuous jet is some of that energy is dissipated by the medium at the
So the energy is dissipated at the end. That's why you see the bright points at the end in many of these things. But it also it's also forced back by the pressure gradient to inflate the lobes, and so it behaves much more like a light fluid pushing the front of the lobe forward. That's what we're seeing in the simulation. So in fact, the jets even in those simulations are much faster than the growth of the lobe, which sort of proves that this is the thing. That's how it works. But yeah, it's a good point. And the timescales, I think this surprised a lot of people because people have quietly revised the timescales for these things on the basis of everything we know now about the dynamics. They used to think, you still get people talking about the lobes expanding relativistically because the jets are going to them relativistically, but that's not actually how it works. The expansion speeds are not slow. Nothing is slow in astrophysics, but they're not anything like as fast as the jet. The material's going up the jet.
Got it. Understand. Okay, thank you for that. Right, I'm going to hand over to the floor, ladies and gentlemen. Anybody got a question for Professor Hardcastle, for Martin?
I'll kick off with one.
On,
given the new sets of data you got from LOFAR, are there any ideas about the proportion of radio galaxies to non-radio galaxies, and can that tell us anything about development of the universe?
Yeah, so I mean, this is sort of bound up with the thing we were talking about before about the proportion of radio galaxies, and as a function of galaxy mass. So we're starting to do that work. You need, because there are so many different types of galaxies, you really need lots of statistics. So I mean, that's something I hope is going to come out of the work we've just been doing to match up the radio and optical data over for the sort of millions of sources. Even then, it's frustratingly hard because we can say, okay, we've got a galaxy, we've got a redshift. Then you might want to ask, what sort of galaxy is this? Is it a spiral galaxy or an elliptical galaxy? That's something that you can't ask that question for many galaxies in the deep universe because the optical data aren't good enough. So we know this is a sort of long-standing understanding that radio galaxies prefer ellipticals to spirals. This seems to be true, but we'd really like to understand how and why in detail. But what we're hampered by is not the radio, it's the fact that we don't know whether these galaxies are spirals or ellipticals because the radio data aren't good enough. And we can't sort of go and get Hubble Space Telescope time for 1 million galaxies and find out. So it's there are some questions we can answer quite easily. There's certainly this relationship with galaxy mass. You see a real, above the sort of about 10 billion solar masses or so, coincidentally about where the Milky Way is. Above that, there's this kind of huge spike up of activity. So something really makes them like massive galaxies. That we do know. I've got some ideas why, but we'd really like to break that down a little bit more, and also to look at things like this, the type of environment they live in. So, do they prefer to live in galaxies that are in groups or clusters? So early studies thought they might, but I think there may be some selection bias. Or are they perfectly happy in field galaxies? Do they care about the large scale environment? Because the jets, of course, are interacting with that large scale environment, or with the hot gas in that environment. So that's something we're working on right now. These kinds of things we can try to answer. But I think we will have a much better picture in a few years. But we're actually, as I say, we're limited by some of the information we have about the galaxies themselves. That WEAVE will help a little bit there. The spectra will help to tell us what sort of galaxies we're looking at. But we could really do with, as always, you need more data. You get one thing good and you immediately think, well, now I'm limited by this other thing. That's just the way it is.
So is the distribution fairly even for what data you have gathered, or are there clumpiness anywhere, or? So,
I mean, the radio galaxies themselves are clustered. I think that's so. If you mean sort of clumpiness on the sky, there are parts. So galaxies themselves are clustered, and radio galaxies follow that clustering. In fact, they're more clustered. Radio galaxies are more clustered than galaxies are. So they have more of a preference to lie in rich environments than just the fact that many galaxies tend to lie in rich environments anyway. So that's telling you again something. Might be telling you about the prevalence of massive galaxies in rich environments, because those massive galaxies tend to form by the merger of a whole bunch of other galaxies. So maybe you just need that dense environment to make those big ellipticals, to make the radio galaxies. Or maybe it's telling us about the influence of the environment on the jets. But certainly the basic the observation is that yes, they are clustered. They generally like, so if you've heard about the sort of the notion of the cosmic web, with filaments and voids and points where the filaments meet, where there are clusters. They like those dense regions. We, again, one of the nice things that we'll be able to do with WEAVE, where you've got accurate redshift for everything, is think about the clustering in 3D space, which is hard at the moment because we don't have good redshifts, which means we don't know very much about the Z direction. We can make redshift estimates, but not highly accurate redshifts for many things. But you'd be able to have to make a 3D picture of the distribution of radio galaxies in space as a function, say, of how bright they are, how luminous they are in the radio, and say, as you go from fainter radio sources to brighter radio sources, do they have more and more of a preference for rich environments, which would be my guess, or actually do they not care? So we don't know that yet, but this is another thing that you could absolutely do with better statistics and slightly more data than we have right now.
Thank you.
Yeah, thank you, Martin. Anyone else with a question for Martin?
Don't be shy.
Anybody? Well, just going back to, you said at the beginning,
sorry, Chris, we lost you.
Yeah, sorry. You said, Martin, at the beginning you weren't going to talk about the Milky Way. Is that simply because there isn't a radio source in our host galaxy, or is it too near, too bright, too intense? What do we know about, if I may ask you about the Milky Way?
Okay, sure.
Silence.
So, yes.
Do we think it has an AGN of some description, or is it active in any way?
At the moment, it's very inactive. So we know a lot about, and this is why it's not an active galaxy in the meaning of the act. So it's a spiral galaxy for one thing. So they tend not to have these radio AGN. But also we know quite a lot about what's going on in the galactic center. So there is this very well studied supermassive black hole around the 3 million solar mass mark, which is actually fairly puny by the standards of the black holes in these massive ellipticals. So the M87 black hole is a couple of billion solar masses. It's nearly 1,000 times more massive than the Milky Way center one.
Yeah.
And that's again probably because of the way that elliptical galaxies grow and grow out of the merger of lots of other galaxies. That's not to say that the Milky Way has always been completely quiescent. Right now, you can if you look very carefully at the galactic center black hole, occasionally it does a little peep of emission, a little puff of something comes out. You see some radio or some X-ray emission. We think the evidence is that currently it's in a very low accretion rate state, so a very small amount of material is falling onto it. Doesn't mean it was always like that. And there's a piece of evidence. There is a structure that you see in gamma rays coming out of the galactic plane called the Fermi bubbles, which looks an awful lot like. So it's coming out of the galaxy is like this, the Milky Way plane is like this, and it's coming out perpendicularly, and it looks an awful lot like something that could be generated by a radio galaxy. And if that's the case, then there might have been some radio AGN activity in the Milky Way tens to hundreds of millions of years ago that we're now seeing the sort of remnants of. So it might have had, it might have eaten something at a high accretion rate state for a while, generated some jets, done the stuff, and then turned off again. If so, that's a piece of good news, because it means that the jets are directed out of the plane. And since we're in the plane, that means if they ever turn on again, they won't be pointing at us. Because jets pointing directly at you would be bad.
Not a good thing. No,
not a good thing.
On the other hand, we're not going to be holding our breath waiting for them to reach.
I don't see any sign, but of course speaking as an astronomer, purely professional point of view, it would be great if they did. If they were pointing towards us, that would be slightly less great. But we don't. It's quite hard to study the switching on of the jets, because they're obviously going to start from zero radio luminosity and get brighter. And if we're ever going to understand how that works, the center of the Milky Way will be the place to do it. But it's as far as we can tell, it's been quiescent, dormant, for tens of millions of years, and the chances of it turning on before I retire, I think, on the limited side.
We've got a better chance of watching Betelgeuse blow up.
Yes, a substantially better chance, I think. Yes, given the odds, that's where you'd put your money, or a naked eye supernova, or one of a number of things before the Milky Way center black hole kicks off. But who knows? And there's always the possibility. One of the way they study these things, the galactic center black hole in particular, is through the orbits of stars, and some of those stars are passing very, very close to the black hole. And if one of those was to go close enough that it could be tidally disrupted, you'd get a flare, which, as the star was basically ripped apart by the black hole, that would be very interesting to study. And you could bet everybody's telescope would be pointing there. Not ours, not LOFAR, because it doesn't go to the southern hemisphere and you can't see the galactic center. But anyone who can see it would be looking at that. So that could happen. There was some suggestion that there might be something of the sort that could happen a few years ago. It didn't, but we live in hope.
Well, yeah, you never know. Okay, if we're all done, anyone got a late question?
I'll have a follow-up question, if I may.
Please do,
so one of your animations showed the evolution of the radio galaxies. Has any of the data from LOFAR managed to fill some of the gaps in to show some of that evolution, or are we still looking more data?
That, I think so. I think we have a pretty good. Yes, there's some quite technical slides that I took out of this talk, actually, which have answered that question. But let me try and describe it. So what we can do if we have images of a large number of radio galaxies, we can do things like measure their length and brightness, and we think that you can. So if you imagine a model, a mathematical model of how a radio galaxy is going to evolve, it starts at zero length and zero brightness, and it obviously evolves upwards. It grows and it gets brighter, and at some point it's going to it turns out it's going to sort of fade away. So there's going to be an upward curve and a downward curve. And at some point, then the jet turns off and it will drop very steeply down, fading very fast while not growing very much. So you can imagine these tracks on this power linear size diagram, as it's called. What we've done, what we did subsequent to the first data release, was to take some models like that. So based on our computer modeling, but kind of made more analytic, and fitted them to data, and showed. So the thing that you don't know in all of that is something we call the lifetime function, which is how long do they stay on for, and what's the distribution of that. So are there many short-lived radio galaxies and only a few long-lived ones, or are they actually basically all about the same longevity, give or take? And so what we were able to show was that if you have a quite sort of uniform lifetime distribution, so they are typically on for long periods, you could reproduce the distribution of sizes and brightnesses very well for the bright end of the radio galaxies, where you can really measure those things very well. So we measured all the sizes, we measured the brightnesses, we basically fitted to histograms of those things, and showed that, yeah, we think we can fit our model to something where, you know, lifetimes are fairly uniformly drawn from a sort of a range of, you know, hundreds of mega years to giga years, which is interesting. And also it's also interesting because there's some suggestion that at much lower jet powers, the lifetime distribution is much different. So there are many more short-lived sources that just turn on for a short while and then turn off again, like we were just talking about with the Milky Way. So we're starting to do that work. There, it would be really nice to have better size measurements, which means using those international baselines of LOFAR to get better resolution, because we're a little limited by how well we can measure the sizes for some of these things. But so we're using size as a proxy of age. We are starting to get a handle on that. And, you know, I wrote a paper about this, so, you know, there's more to come. I've got one of my postdocs is working on this problem right now. So, yeah,
Thank you.
That's very much one of the things we want to do.
Excellent.
Okay. It sounds like we're done. We all done? Gone? Okay. Well, once again, I'll just stop the recording here.